Hello everyone. So in this set of notes, we're going to introduce the concept of a limit. So as we're going to see, limits are very important to the concept of calculus and to the concept of basically just understanding what we're doing with calculus. So for the next several sets of notes, several topics, we are going to focus on this idea of a limit. So in this first set of notes, we're not really going to get too much into the calculation aspect of limits. We're basically going to talk about what a limit is. We're going to talk about this distinction between what we call a one-sided limit and a two-sided limit. And rather than really doing any sort of calculations here at the start, we're mostly going to be looking at limits visually. So we're going to talk about using some graphs, some visuals, graphs of functions, and we're going to use those to determine the values of limits or to determine if a limit does not exist in a given case. And we're going to talk about, of course, what that means here as we go. So like I said, the idea of the limit is really important in terms of understanding the logic behind calculus. Sometimes when you get into calculus, you sort of jump into it and you're not really sure, like, what are we doing this for? What does calculus actually give us? Why do we care? Why are we using this type of math? And so understanding the idea of a limit as a base, I think really helps make the rest of the course make sense in terms of like what our ultimate goal is when we're applying calculus, when we're using calculus. So as we'll see as we go forward, there's going to be two main operations or branches to calculus. We're going to talk about differentiation and integration, uh, and we're going to see that behind the scenes, the idea of the limit is really going to be important to us. So the whole thing that we're getting at here is how do we describe how a function behaves? So let's sort of start at the very beginning here and talk a little bit about some of the basic things that we need to know or remember or recall in order to proceed forward and talk about the idea of a limit. And these ideas, these terms, all have to do with this idea of a function. So if you're not super familiar with a function, I would recommend going back into the textbook and reading a little bit more about functions. Here on page 2, I have a note saying that in our CLP textbook there is this review section on functions and things like domains and ranges. So if this is not enough of a review for you, I recommend that. But just to get us into things, let's do a very brief review of some of the terms and the ideas that we're going to see when we start talking about functions and limits and eventually the main pieces of calculus. So let's start by considering a situation where we have some quantity of interest that we care about, but maybe this quantity is not, for whatever reason, consistent within the problem itself. So it's a value that's important to us, but maybe it's just not constant. Maybe it can change due to certain conditions about the scenario or the problem or the experiment, or there's some other reason why it differs from situation to situation. So it changes, but we still care about it. So we still want to be able to represent that quantity in an equation or in a formula. So instead of using, say, just a number for that quantity, we basically use a placeholder for it. And these are usually where we start seeing our letters in math, right? Our x's, our y's, our z's. These are things that we usually are usually used to denote variables. So a variable is, as the name suggests, a quantity that can vary from iteration to iteration or scenario to scenario within a given experiment. This X or Y or W or Q or whatever letter we're using is basically just a placeholder representing where that variable plays its role, say in a larger equation or in a function or in just general talk about the scenario. So a couple quick examples here of things that you might consider a variable. Let's say x represents the time since an object was dropped from the top of a building. So x, as you would suspect, would vary depending on, of course, how long it's been since you've dropped the object from the building. It could be 0 when you haven't dropped it yet. It can be 5 when it's been 5 seconds, 8 if it's been 8 seconds, etc. We could also have something like the altitude of a plane. So this, of course, will vary depending on where the plane is. Maybe you're in the takeoff process and x is increasing. Maybe you're in the landing process, x is decreasing. It's varying, it's variable. It's different from second 1 to second 2. Or we might have something like this, a little bit less of a physical example, but maybe it's representing the number of units of a product that are sold by a company or a warehouse or something like that. So maybe it's representing the number of units sold per hour, let's say. So maybe at noon, this company sells 5,000 units. At 1, this company sells 8,000 units. So X may vary from hour to hour or whatever time span you're using to count the number of units. So sometimes you might just see your variable on its own. X is standing in, or Y or Z or whatever, is standing in as a placeholder. But oftentimes, and this is especially what we'll start seeing in this class, we want to describe how other quantities change as X changes. So maybe there's some other value that we're concerned with, and we want to see how that changes as X itself changes. And the nice thing about this is we can actually express the relationship between X and this other quantity using a function. So a function is just a fancy name we give for a rule that associates some sort of output with a value of X. So you can really just think of a function as a rule. We often write it in terms of some sort of, again, another letter or some other expression involving a name or something like that. But you can really think about it as you give something to the function and the function gives something out. So a very common way that we see functions written, if the function named f, we can see it written as f of x, if x is the input to the function. So a really simple example of a function would be, say, f of x equals x squared. So this is telling us a rule. It's telling us for whatever input we give it, whatever this value of x is, it's going to give us a specific output. Now, whether it's a unique output for every input, we'll get into that more later. Specifically, an actual function is one where a one-to-one function is one where there's a unique output for every unique input, but we'll get into that a little bit later. For now, just think about this sort of thing as we're giving something to the function, it's giving us something back. So for example, if we give it an x value of 4, what that's telling us is if I put in a 4 here for my x, then everywhere I see an x for this output expression, I'm going to replace it with a 4. So this would become 4 squared, x becomes 4 squared, and the output for an input of 4 is 16. Sometimes it helps to think of functions themselves as another variable. So once we start graphing things now and a little bit later, you might also see functions expressed as, say, y. So maybe y equals x squared. It's the same thing, it's just we're not representing the function with the function with the input of x, we're just giving it its own variable name, but it can mean the same thing, it's just written in a different way. So those examples that we saw up here, where we were talking about just different inputs, different types of x's, different types of variables, we can also talk about associated functions for those variables. So if x is the time since an object was dropped from the top of a building, we could think of a function where we give it a value of x. So for example, maybe the function f of x is the position of an object as a function of the time x since the object was dropped. So a function of x. For our second x up here, x being the altitude in feet of a plane, so how high the plane is above the ground, f of x could represent the surrounding atmospheric pressure as a function of the altitude. So we give this function, however it's constructed, a particular altitude, and it will spit back the computed surrounding atmospheric pressure. Or finally, if x is representing the number of units of a product that are sold, say over a certain amount of time, then we could also talk about a corresponding function we might be interested in. The total profit as a function of the number of units sold. So we give it the number of units sold, whatever this function equation or expression is, and it spits back the total profit based on, in part, that number of units sold. And again, If you're like, oh, okay, well, I kind of remember this stuff, but I'm a little bit shaky, I would recommend taking a look at this piece of the textbook. So it's one of the sort of intro chapters. It's pretty short, but it is pretty comprehensive. So I would recommend looking at that. If especially as we go forward, you're like, oh, maybe I'm not too sure about how functions work, this would be a good place to review. So these examples that we just looked at are sort of real life examples, and there's an abundance of these that we could use in, say, physics, finance, chemistry, music, things like that. But as we'll see, for the purposes of introducing a lot of this stuff, especially here at the start, we're going to basically rely on just some generic functions. We might not know exactly what they're doing. We might not know what x is. We might not know what the function is. They're mostly just there to help us demonstrate the concepts that we want. So for example, we might see functions like these where we're not explicitly telling you what x represents or what f of x represents. They're just kind of there for the purposes of learning. We will see some actual real life functions sometimes, but for the purposes of most of this intro stuff, we're just going to be dealing with generic functions where we're kind of pretending we don't really care what x is, we don't really care what the function is in terms of real life consequences or impact. We're just using these as examples. Demonstration. So as an example, let's look at this last function here. Let's look at this in a little bit more detail to introduce a couple ways that we could describe the behavior of a function. So for our purposes right now, when we talk about describing the behavior of a function, and again, this is going to be really, really helpful for us when we introduce limits here in a second, we can talk about describing the function's local behavior and long-term behavior. So how does a function behave locally? How does it behave over the long term? So let's start with local behavior first. So when we talk about the local behavior of a function, we're talking about what happens to the function as the input, the x, approaches a specific number. So we have some specific value of x we care about, and we want to know how the function behaves as we get closer and closer to that specific value of x. So let's again look at this function. F of x equals 1 over x plus 1. We want to describe the local behavior of this function, which means we want to describe it as our variable x approaches a certain number. And in this case, we want to describe its behavior as x approaches 1. Now, could we just plug in a 1 here for our x, so f of 1, and get 1 over x plus 1, which would be, well, x we're saying is 1. 1 over 1 plus 1 would be 1/2. Well, yeah, that's how the function is behaving at 1, at x equals 1. But we want to talk about, and again, important when we talk about limits, what the function is doing as x approaches 1. So to help demonstrate this, I've got this little table here. So notice I've got two things going on here. I've got values of x, and I've got the corresponding values of the functions for those values of x. So for example, in this first row, my x value is 0.9. And so what I'm doing to calculate this is I'm taking my function at 0.9. Which means every place I see an x in my function, I'm going to replace it with 0.9. So this is going to be 1 over 0.9 plus 1, which gives us, if we were to calculate it out with a calculator, approximately that value there. Same thing for 0.999. Let's do one that's getting close. So again, we're trying to approach 1 here. So notice we're getting a little bit closer and closer and closer to 1 with these first three values of x. So to fill in this missing cell here, we are finding the value of our function at 0.99999, which, just like we did up here, I'm going to plug in that 0.99999 every place I see an x in my function. So this is 1 over 0.99999 plus 1. And if we calculate that, we would get 1.500002 1.25, just rounding to the same number of decimals as I've got in these other boxes, just for consistency's sake. And we can see it looks like the value of the function is approaching what it looks like it is if we just plug in a 1. So it looks like we're getting closer and closer to 1/2 if we approach 1 from values less than 0.1 or less than 1. We can also look at this from the other direction. So what happens if we start with a value a little bit above 1 and start plugging in values again closer and closer and closer to 1? So here the value that we start with is 1.1 for our x. So this is f of 1.1, or 1 over 1.1 plus 1. Same exact thing I was doing up here. And that gives me this 0.4761905. Here's 1.001, a little bit closer to 1. Here, let's get really, really close. 1.00001. Let's see what this value is. So plugging that into my function, I get 1 over 1.00001 plus 1. And again, if we were to calculate this out on a calculator or something, we would get 0.499975. Now again, notice we didn't calculate this function at 1, but we can see that we're getting pretty close, right? If we kept getting closer and closer, we would get our x values closer and closer to 1. And it looks like our function value from both sides, from less than 1 and greater than 1, is going to approach 1/2. So f of x approaches 1/2 as x approaches 1. That's basically what we've shown here, without doing any sort of calculations or anything like that, other than just filling in this table. So that's a description of the local behavior of this function as x approaches 1. It looks like the function is going to approach 1/2 as x approaches this specific number. Now, the other type of behavior we can talk about describing is the long-term behavior, and I've got that on the next page. The long-term, contrasting to the local, the long-term, sometimes called the end behavior of a function, describes what happens to our function f of x as x increases or decreases without bound, or in other words, as x goes toward either positive or negative infinity. So sometimes it's easy to think of infinity or negative infinity as an actual number. It's technically not. Sometimes it's helpful to kind of treat it like that, as we'll see later, but it's not. Remember that it's not a number. Think about infinity as a behavior. So when we talk about negative infinity or positive infinity, we're talking about a quantity that's either increasing or decreasing without bound. So it's just continuing to increase, either in the positive direction or the negative direction. So just remember that as we go forward, this idea of we're not approaching a specific number or a very, very big number with this idea of infinity. We're just saying x or whatever is continually increasing. There's no stop to how big it can get. I'm getting a little ahead of things with that, but just to talk about that, since that's our first time seeing infinity so far. So let's go back to that function we were just talking about. So we just described its local behavior for an x value of interest of 1. Now let's describe the long-term behavior of this function as x approaches, let's say here, positive infinity. Or in other words, as x increases. It's been a while since I've written on this tablet, I apologize. Increases without bound. So it gets bigger and bigger and bigger in the positive direction. And so once again we have a table, but now I'm just randomly starting with a pretty small x of 1, and I'm just making that x value get bigger and bigger and bigger, increasing without bound. And just like we saw in the previous table, these corresponding f of x values are the values of this function for those different values of x plugged in. So in this case, we're missing these two cells here at the bottom where we've got these two largest values of x in the table. So let's start with this one. What is that, 100,000? So we're going to figure out what f of 100,000 would be. And just like we were doing in the previous table, what we're going to do is we're just going to plug in that x value into our function. So 1 over 100,000 plus 1. That's going to give us 0.00001 as my function value. For this last one, that's 1 million, same thing. F of 1 million is 1 over 1 million plus 1. And that's going to give us an f of x value of 0.0000501. Now we're starting to see a pattern here, even with just this few numbers of values of x that we're plugging in. Notice we start with an x value of 1/2, but as we start to increase, f of x value of 1/2, but as we start to increase our values of x, f of x really starts to decrease, and it looks like it's approaching 0, at least from the work we've done so far. So I could say here, f of x approaches 0 as x, I'm just going to say here, increases without bound. Now just to kind of put this all together, let's visualize this function. So what does 1 over x plus 1 look like? What is this thing? Well, on the bottom of this page here, I have a visualization of this function. So this is again where it helps to kind of think about x as values along your x-axis, so the input along your x-axis, and the output as the values on your y-axis or your vertical axis. So these are values of f of x. So we talked about local and end behavior. So with the local behavior, I'll use some color here. We talked about the local behavior at x equals 1, or as x approaches 1. So if we think about this visual, here's the value of x that we care about. We can see just from the graph that as x approaches 1, as we get closer and closer to 1 here from either side, notice that our function looks like it's approaching a specific value as well, whatever this value is, which looks like it's 1/2, like we said with our calculations or our table. So as x approaches 1, our function value approaches 1/2. And in terms of the end behavior, we were talking about what happens as x increases without bound. So in other words, if we were to continue this x-axis way, way out there, what would this line look like? What would this function be doing? And as we talked about or showed with our table here, what we showed with this table is it looks like our function value is getting closer to 0. Or in other words, it looks like this line is going to keep going closer and closer and closer and closer to our axis here, going to 0. So for the end behavior, it looks like this is going to just keep going and getting smaller and smaller and smaller, closer to 0. Now, we did a lot of work here, right? We looked at some tables, we looked at some visuals. This is all to really get us set up for the idea of what a limit actually is. So on the next page, let's actually now talk about a formal definition of this idea of a limit, and then link this to what we were just doing with another example here, another picture. So here on page 4, we're going to talk about the formal definition of the limit. So in order to get our formal definition of our limit, we do need a couple more things. Let's define our generic function as we have been, so our f of x. We're also going to need some point, let's call it a. This doesn't necessarily have to be in the domain of f of x, just consider some point. Now there's a couple ways that you can visualize this, and the specifics of this we're going to get into a little bit more later when we talk about continuity and things like that. But for now, just like on the previous graph that we saw, I found my cursor here, let's look at the same sort of setup. So our x is still on our x-axis and all these visuals, and our f of x is plotted by this little line here in blue. Now it's kind of hard to read on this screen. Maybe it's not too bad on yours, but this is our a. This is some value of x, some point on our x-axis a. Now, a could land on our function, which is fine. It could be off the line of our function, which is also fine for our purpose right now. We could also have this open circle here. What I'm trying to emphasize with these pictures, if you're like, what's the difference between all these? Don't worry about that too much right now. I'm mostly just saying all we need to define our limit is we need some value a, and we need some function f of x, where a is some value of x. The big thing we're trying to answer here, or the big thing that we can do with limits, is it tells us what happens to f of x as x approaches a. So as we get closer and closer to this value of a, what's our function doing? How's our function behaving? That's the idea behind a limit. So again, let f of x be our function. Let a and this capital L be just real numbers, things that exist. We say that L is the limit of the function as x tends to a if we can make f of x close to L by letting x get close to a. That's a mouthful, right? That's kind of like the textbook definition of a limit. I think it's a lot easier to break it down visually and piece by piece in terms of how you'll usually see this written. So in terms of like the mathematical expression that you'll usually see for a limit, you'll usually see something like this. So I think the easiest way to understand what a limit is what is happening to our function as the input gets closer and closer to a. Or another way to say this is the limit of f of x as x approaches a. And let me make that a little bit more precise. Instead of this, I'm going to say capital L. L is the limit of our function as x approaches a. So L is a specific value, some number, some quantity. L is the limit of our function specifically as x is going towards something. So to kind of break that up into the pieces of this expression, the limit value is capital L. Where are we looking for that? We're looking for it for x values close to a, and whatever our function is just this f of x. Now there's a couple other ways that you can write this or express this, and it means the same thing, they're just a little bit different with the language. Same thing, f of x goes to L as x goes to a. F of x goes to L as x goes to a. Or maybe a little bit symbol-y or more symbol involved, f of x goes to L as x goes to a. They all mean the same thing, they're just written slightly differently. And all of these expressions, all of these things are getting at the same idea. What is happening to f of x as x approaches but does not exactly equal a? And sometimes this is the tricky thing with limits, and we'll see this with our example here in a second. We don't really care about what's going on at a. which is kind of contradictory because it's in our expression and we're dealing with it. But when we talk about a limit, we're really talking about what's going on close to a. What is going on with our function as we get towards a, not exactly at a. So I'm going to leave that definition up there, and let's take a look at a couple examples using this picture. So on the bottom of page, what are we at, 4, I have this picture of a function. So this is, for those of you who remember the term or are familiar with the term, a piecewise function. If you're not totally sure with what that means, we'll talk about it in more detail later. But for now, this is the graph of the function f of x. It's a messy looking function. There's lots of little sections or pieces to it. But we're going to use this function to determine the values of these different limits. So again, think of these graphs as our values of x on our x-axis, and on our y-axis or vertical axis, that's representing the values of our function. Now let's start with the first one, and I'm going to color code these so they're a little bit easier to see. Let's start with the limit here. Now I'm going to say these out loud, kind of using the language you tend to use when you're saying something about a limit or saying this expression. We want the limit of f of x as x goes to 1. So just saying that again, we're calculating the limit of f of x as x goes to 1. That's a very typical way of saying this expression out loud or writing it if you were to write it out. So this 1 is like our a. X is getting close to something, 1. What is the function doing near that value of x? Near x equals 1. So I'm going to go up to my graph here, my picture, and again, my x values are along my x-axis, and in terms of what this picture represents, each of these tick marks is a unit. So x equals 1 is this unit, or this notch right here. Now, it's not super exciting what's going on with our function, because if we look at our function as we're in sort of this neighborhood, our function's just this little straight line down here. But in terms of figuring out the limit, that's actually nice and easy, because if we look at this function, and actually I am going to draw a kind of a little box around here. This is like the neighborhood of x equals 1. I can see that as we get closer and closer to 1 on my function line, my function value is actually not changing. It's staying at, it looks like, -1, -2. My function looks like it is behaving as a value of -2 around x equals 1, which means the limit of this function as x approaches -1 is -2. And that's typically how we write the solution or the value of the limit. We say the limit as f of x, limit of f of x, x goes to 1, is equal to whatever that value is, in this case -2. So the function is just sitting at -2 as we get closer to x equals 1. Let's look at this one. So again, reading this out loud, we want the limit of f of x as x goes to or approaches -2. So x of -2, that's going to be over here, -1, -2. Now this one looks maybe a little bit more complicated. Let me again draw my little window or my neighborhood here. Now, it looks like we have this function defined specifically at x equals -2. We have this open circle up here, but we have this filled in circle here, which suggests that at -2, my function value is 0. So this is the point -2, 0. So it's tempting to say, oh, the limit of f of x at -2 is 0, because at -2, my function value is 0. But that's not what we care about with limits. And again, this is sometimes the thing that's trickiest with limits, because it might take a little bit of time to get used to. With limits, We care about the behavior of our function as x approaches but does not exactly equal whatever our a is. So in fact, when I'm calculating this limit or looking for this limit here for this second part of the question, I don't care what's going on at -2. I care about what's going on near -2. What's my function doing as I get close to -2? And as I can see from my graph, let's start from this side here first. As I get closer and closer to -2 from this side, it looks like my function value is getting close to, oh, what would that be? 1, 2, 3.5? Same thing from this side. So as x approaches -2, my function value is approaching not 0, but 3.5. So that's my limit. Again, I don't care about what's going on at a, at -2, at 1. I care about what's going on near it. What our kind of intuition was when we first looked at this point is actually what this question is asking here, part 3. So notice there's no limit in here. We're not calculating a limit. This is just asking us what is f of -2. And this is actually what we were just talking about with this point. So instead of calculating a limit, if we see an expression like this, f of -2, this is actually just asking us what is the value of the function at -2. And we just said that going through part 2 of this question. Well, we've got this filled in circle here at x equals -2. This filled in circle is at an f of x value of 0. So f of -2 is 0. So be really, really careful with that when you're talking about limits, and we will get a lot of practice with this in the next set of notes as well. When you're talking about limits, you don't really care about the a. You don't care about the number in the x expression. You care about what's going on around it. That's a really, really important thing to remember, and that's going to come up over and over and over again as we talk about limits, as we talk about the idea of what we can do with limits and what we can do with calculus. Now, for some people, it's been a while since you've read a graph like this, or maybe you're like, oh crap, I don't remember what the open circle means versus the closed circle. Again, if you need a little bit of a refresher on that, you can look at the textbook, but just for our sake here, a closed circle on a graph means the function takes on that value at that quantity at x. Open circle means that the function does not take on that y value at x. So we'll kind of see that here in the next example as well. But just a reminder about the notation with graphs. So let's do a bit of a longer example here. So we have another graph. This is a graph of let's say, another function f of x, and we're going to use it to find quite a few values here. And then we're going to use the example from the previous page and this one to sort of make some conclusions, some remarks about finding limits and what limits actually represent. Let's see if I can get this just right so we can see everything. Okay, there we go. So let's start with this. So again, here's my x values on my x-axis. You can think of this as f of x on my y-axis. And let's start with the limit of f of x as x goes to 1. So here's my x value of 1, and again, I'm just going to draw on my picture what my function is doing as it gets closer to 1. So I'm going to start going in this direction. As I get closer to 1 from this direction, looks like my function is approaching a value of 2. If I go from this direction, oops, let me draw that back in there, it looks like my function is approaching the same value, 2. F of 1 is 2. That's the value at 1. I care about the limit, so I'm not really caring too much about this point. I'm saying what's going on near that point. Well, the function looks like it's approaching 2, so my limit here is going to be 2. What I just said, f of 1 is 2, is what the second question here is asking for. F of 1. What happens to my function if I plug in a 1 to it? So f of 1, there's a solid, it's kind of hard to see because it's not distinct point, but you can think of this solid line as meaning there's a solid point right there on the graph. So f of 1 is that value of 2. What about this one? The limit of f of x as x goes to 2. So here's 2, and again, let's draw on our picture. So if I approach 2 from the left-hand side, looks like my function's going to 3. And if I approach it from the right, this direction, it looks like my function's going to 3. Do I care about the fact that there's an open circle there? No, I do not care. I just care about what the function's doing as I get closer to 2. So even though there's an open circle there and there's this filled in circle up here at 5, my limit's not going to be 5, it's going to be the 3. It's going to be that value that the function looks like it's getting closer to as we get closer to 2. What about this one? The limit of f of x as x approaches 3. And this is sort of the same thing. We see an open circle there at 3, so we're like, oh, maybe there's not a limit there. But we don't care about what's going on at 3. We care about what's going on close to 3. So if I approach from this direction, it looks like my function is approaching a value of 4. If I approach from this direction, it looks like my function is approaching a value of 4. So even though there's an open circle there at f of x, or at x equals 3, my limit is still going to be 4. What about f of 2? So again, it's not a limit. There's no limit notation there. It's asking us for what is the value of the function when x equals 2. And we sort of talked about this with this part 3. At x equals 2, I have an open circle at 3, so that's not where my function is defined at x equals 2. I have a closed circle up here. So actually, f of 2 is not going to be this open circle at 3. It's going to be 5 because we have that closed circle there at 5. So this is like the point 2, 5. And then finally, what about this one, f of 3? So f of 3, we had another open circle, but we don't have a closed circle anywhere. So we're going to say that that function is actually undefined at 3. There is no point where I can basically draw a line through or mark a point and say that's the function value at 3. It doesn't exist. It's undefined. Once we talk about limits existing or not, I'm going to come back to this. But for now, I'm just going to say f of 3 is undefined. Now from this, and the example on the previous page, let's look at a couple important remarks here. One thing that's important to note is the limit of f of x as x goes to a doesn't necessarily equal the function value at a. Right? We just saw that with parts 3 and 5. The limit as x goes to 2 is 3, but the function value at 2 is 5. They don't necessarily have to be the same thing. Another thing, the value f of a might not exist for a particular function, but the limit at a might. We just saw that with parts 6 and 4. F of 3 is undefined, but the limit as x goes to 3 is a thing, it's 4. So your f of a may not exist, but the limit at a might. That's perfectly valid. Now the big one, and this is the one that I keep mentioning, and I'm going to put a bunch of stars by it because it is very important. The value of the limit as x goes to a of f of x depends on the values of the function near a, but does not depend on the value at a. So again, we don't care about what's going on at a when we're calculating a limit. We don't care. We just care about what the function's doing near a. Now, in the above examples, we saw cases where the limit exists. We can see it, we can visualize it, and later we'll see we can calculate it. But there are situations where you might not have a limit. Just like there are situations where a function might not be defined, you'll have situations where you might not have a limit. So to understand that, we need to understand one-sided limits. So let's take a look at that on page 6. Let's look back at example 2.11, so that function that we've been talking about, but let's modify it just a little bit here in terms of what we're looking for. So back in example 2.1.1, let me scroll back up there. We were describing the local behavior of this function as x approached 1. So this was the bottom of page 2. Now we're doing the same thing almost. We're describing the local behavior of this function, but now we're saying as x approaches 1 from the left. So what does that mean? That's our modification here. The wording here is telling us that we're actually looking for what we call a one-sided limit. So I'm just going to draw a little number line here, a very, very simple number line with just 1 on there. When we're saying describe the local behavior of this function as x approaches 1 from the left, we're saying what is happening to this function, what is the limit of this function as x approaches 1 specifically from the left side. So in terms of values, x is getting closer and closer to 1 but still remaining smaller than 1. That's what we mean by approaching from the left. So like this is, I don't know, 0.9, 0.8, etc. So a one-sided limit is the same thing as a limit in terms of the idea, but now we're just talking about the behavior of a function from a specific direction, either from the left or from the right. So we can have a left-sided limit or left-hand limit, right-sided limit or right-hand limit. So let's give those two things a little bit more formal definitions. So left-handed limits, which I usually, and you'll see this other places as well, abbreviate LHL because it's much faster to write. A left-hand limit describes the behavior of a function as x approaches a from the left, or from values smaller than a. So the definition is the same thing in terms of that formal definition of the limit. It's just now we're talking about a specific side or specific direction of approach. So just like we drew above, if this is our number line and this is our value a, whatever it is, we're looking at the behavior of the function to the left of a, or as we get closer to a from the left. And we see a little bit of change in our limit expression as well. Notice that this is now a with a superscript negative sign. This is specifically saying we're looking for a left-hand limit, or x approaches a from values of x less than a, from the left. And right-hand limits, as you can probably guess, mean the same thing, just from the other direction. So a right-handed limit is one that describes the behavior of our function as x approaches a from the right, or from values larger than a. So again, same idea, but now we're approaching a, or we're looking at how our function behaves as we approach a from the right, so from values larger than a. And in terms of our notation and our limit expression, we usually see this with an a, or whatever the number is, with a superscript plus. So this is x approaches a from values of x greater than a. Right-hand limit, or RHL. Much faster to write. Now, the idea of one-handed or one-sided limits is important because we basically need them to determine if we can say if a limit actually exists or not. So keeping these directional or one-sided limits in mind, on the top of page 7, let's talk about how we can say if a limit exists. So when I say a limit, I'm just using the plain word limit, not right-handed or left-handed. I mean a two-sided limit. So the ones we were talking about at the beginning. So here's our first theorem. Let f of x be our function. Let a and l be real numbers like we've defined before. Let L be finite, so it is some number that exists. This limit, the limit of f of x as x approaches a, exists if and only if both the left hand and the right hand limits exist and they're equal. And they both equal L. So basically, here's our left hand limit. This equals our right hand limit, whatever it is. And they both equal the same thing, which is our L, our actual limit value. So, in other words, L is the limit of our function if both the left hand and the right hand limits agree, I guess technically exist and agree. If they don't, we say the limit does not exist. And we usually write that like this. So the limit of f of x as x goes to a, dne does not exist. Notice there's not an equal sign here. We're not saying it equals it does not exist. We're just saying it does not exist. So let's put all of this together so far. Let's look at another function graph and let's find some limits, some one-sided limits, and just see if we can put all this together. So here we have a function g of x. So here's our x values, here's g of x on our y-axis, and we're going to determine the following 6 quantities. So let's start with this. So the first part is we just want to find g of 1. So not a limit, just the value of the function at x equals 1. Here's x equals 1. We've got a couple open circles and a closed circle, and like we were talking about, where the open circles are, the function is not defined. But if there's a closed circle, that's where the function is defined. So at x equals 1, g of x equals 2. Now let's find a one-sided limit. Note, be really careful now that we're talking about one-sided limits. Make sure to pay attention to see if you have a superscript in any of those limit values, those a's, just to make sure you're calculating the right type of limit. So here we want the limit of g of x as x goes to 1 with the superscript plus. And remember, that means we're specifically caring about what the function is doing as we approach the value from the right, so from values larger than that. So where's my 1? So here's 1. I want the limit as x approaches 1 from the right. So if I look at my function and I look to the right of this 1, I can see that here's my function, and as I move closer from the right hand side, my function looks like it's approaching 5. There's an open circle at x equals 1. We don't care, we're calculating a limit. So it looks like the limit as x approaches 1 from the right is 5. What about from the other direction? The limit of g of x as x approaches 1 from the left. So we still care about what's going on close to x equals 1, but now we're approaching it from this side. So if I look at my function as I'm getting closer and closer from the left-hand side, it looks like my function value is approaching a 4. So the left-hand limit as x approaches 1 from the left is 4. Now let's find a regular limit, or a two-sided limit. The limit of g of x as x goes to 1. Well, this is what we were just talking about above. We need to consider the one-sided limits to determine if a two-sided limit like this exists. Remember, from above here, the left-hand limits and right-hand limits have to agree at the point of interest, at the x value of interest, in order for the limit, the two-sided limit, to exist. Here, We just calculated the left and right hand limits, and we saw that they did not agree. So that means that this limit as x goes to 1 does not exist. And the reasoning here is because the right hand limit does not agree with the left hand limit. And we can kind of make sense of that with our picture, right? I can't show this because I can't show my hands. But if you think about kind of tracing this from both sides as you get closer and closer together, your fingers or your pens aren't going to match up. They're going to be in different places. So that two-sided limit, because of the disagreement there, because of that jump, is not going to exist. What about the fifth one here, g of -1? So now we're over here, we're not calculating a limit again, we're just finding the value of the function at -1. So again, I'm going to consider my function. I've got an open circle here, I've got a closed circle here. I'm going to look at the closed circle. At the closed circle, my function is a 3. Function value is a 3. So g of -1 is 3. And then finally, one more limit here, one more one-sided limit. We want the limit of g of x as x goes to -1 from the right. There's that superscript plus. So I'm going to keep considering this -1, but I'm going to approach it from this side. So from the right. So if I consider what my function is doing from the right, as I get closer and closer to -1, it looks like my function value is approaching, what was that, 2. So my limit here is 2. So that's this general idea behind limits, behind one-sided limits, two-sided limits, limits existing or not. Now there's a couple other things I want to mention here, and we'll do one more big example at the end, specifically about what we call infinite limits. So if we look at all the limits we've calculated so far, this 5, this 4, this 2, up here earlier we had a 2, a 3, a 4, all of our limits so far have been finite. They've been numbers. However, it is possible for the limit of a function to be infinite. So you can have a limit that's positive or negative infinity, just meaning that the function is going to keep increasing or decreasing without bound as you approach a specific value. So for these I've drawn some pictures because I think these are a little bit easier to see. But basically the idea here is now we're looking to see if our function's going to just like shoot off to positive infinity, keep getting bigger and bigger and bigger, shoot down negative infinity, keep getting smaller and smaller and smaller. We can talk about this in terms of right and left hand limits or two-sided limits. We can say that the left hand limit of our function is infinity if we can make the function as large as we'd like by just getting closer and closer to a from the left. So as we can see in this picture here, I'm getting closer and closer to a. Notice this function is just shooting off. A is acting like a vertical asymptote, if you're familiar with that word and that idea. If not, that's fine. We'll talk about them later. But basically, the function's not crossing this line. It's just shooting up and up and up. So my limit value is infinity, increasing without bound. Same idea for negative infinity. My limit's going to be negative infinity, my left-hand limit, if we say that the function can be made as small as we'd like as we approach a from the left. So here again, I'm approaching, but now I'm shooting off down, going that way, not hitting a, so my limit here is negative infinity. Same idea with right-hand limits, nothing really too new here. Infinity and negative infinity, again, I think it's easier to see with the pictures. Now I'm approaching a from the right, and in my drawing, my function is shooting up and up and up. It's not crossing a, it's just getting bigger and bigger as we get close to a. That's going to give me a positive infinity as my limit. And then negative infinity for my right-hand limit can occur if, again, I'm approaching from the right, but now my function shoots down. Down, down, down. I don't cross a. It's a vertical asymptote. My limit is negative infinity. And just like we saw with the finite limits, we can also have two-sided limits that are infinite. So I could have a two-sided limit that's infinite, infinity or negative infinity, if both the left and right-hand limits agree either to positive or negative infinity. So shooting off up from the left and from the right, that gives us a positive infinity. Or I don't have it on here, but I'll just draw it. If we approach A and we shoot down in both directions, the left hand and the right hand limits, that gives us a two-sided negative infinity as our limit. Now, again, we're not really doing any calculations in this set of notes. Those will come later. So we'll see this in a graph in just a second. But I do want to mention one quick thing here, just because this is sometimes something that disagrees with other textbooks or maybe other ways that people have been taught. And I just have this note on here so that we're consistent within this class in terms of how we're stating limits. So technically, a limit only exists if the left-hand limit and the right-hand limit equal L, and L is finite. So technically, when we have a positive or negative limit in terms of our limit value, they technically are cases where the limit dne does not exist. So in other words, infinity, like we said, is not really a number. It's this idea of unlimited, unbounded growth. So technically, when we have a positive or negative infinity for this L, technically the limit does not exist. But, and I'm going to put a little star here, for the purposes of this class, we still like to specify when we've got limits being positive or negative infinity, just to distinguish them from the cases where the right hand and left hand limits just don't agree. So technically these are both cases where the limit does not exist, but we're just distinguishing them. So even though technically an infinite limit is a case of does not exist, we still like to denote it as being either just positive or negative infinity to show that our left and right hand limits are still agreeing. So we can say the limit is infinity or negative infinity. We are not writing these as dne just for this class, just to be consistent. So technically these are dne's, but for the purposes of this class, if you have an infinite limit, write it as either positive or negative infinity, whichever one, of course, is appropriate for the case. All right, so let's do one more example here on the bottom of page, whatever we're on, 10. We have another function, f of x, and we're going to use it to determine the following 6 values here, all limits. So as always, let's start here. So the limit of f of x as x approaches, again, be careful, -2 from the left, that superscript in negative here, it's a little bit involved because we have the negative for the -2, then we have this negative afterwards. It's the negative or the plus after that's indicating if it's a one-sided limit. So this is -2, and we're approaching it from the left. So if we look at our picture, and all of these tick marks are 1 unit, just like in the previous examples, this is the same one we've seen before. Here's -2. Now we're approaching from the left, so we're approaching from this direction. As we can see, as we get closer and closer to -2, it looks like our function is going up and up and up, and approaching this value of 1, 2, there was that 3.5 that we saw before. So my one-sided limit as x approaches -2 from the left is 3.5. This next one, the limit as x approaches -2, but now from the right of f of x. So now we're approaching the same point, this -2, but now we're going from this direction. So again, kind of creeping along here, I start seeing my function. As I get closer and closer to -2, my function again gets closer and closer to 3.5. So this right-hand limit is also 3.5. which means in a case like this where I want the two-sided limit, or the limit as x approaches just plain old -2, I can use my picture, I can use these two results. These two results agree and are finite values. So I can say that, well, since the left-hand limit and the right-hand limit agree, then this two-sided limit is going to be that value they agree upon, 3.5. In other words, my left-hand limit equals my right-hand limit. The fourth one, the limit as x approaches 4 from the left of f of x. So where's 4? 1, 2, 3, here's 4 as my x value. I'm approaching from the left, so I'm approaching from this direction. Oops, sorry, from the left, this direction. And for that, I'm going to go down here. Notice that my function is just this straight line here, pretty boring part of the function. And as it approaches 4, my function value stays at -2. So this limit here is -2. What about the limit as x goes to 4 from the right? So we're still approaching this 4, but now go from the correct direction, we're going from this direction. And we can see that my function starts to approach 4, but then it looks like it shoots way up here. It doesn't look like it's going across the 4. It looks like, again, that vertical asymptote, for those of you who are familiar with that. It looks like my function is shooting off up and up and up, positive infinity. It's increasing without bound. So this limit is going to be our first infinite limit, positive infinity. We'll see a bunch of those as we go forward. And then finally, number 6, the limit of f of x as x goes to 4. So it's just plain old 4. So just like we did for the third one over here, I'm going to look at my two results. Here's my left-hand limit, here's my right-hand limit, and they do not agree. I've got a -2 and I've got an infinity. And when my left and right-hand limits don't agree, remember that's the case where the limit does not exist, DNE. And that's because the left-hand limit, in this case, does not equal the right-hand limit. So there's kind of our visual introduction to limits. In the next couple sets of notes, we'll include, of course, more visuals, but we're going to start getting into how do you do this if you don't have a graph? How do you calculate the limit of a function rather than look at it from a picture? In the next couple sets of notes, we'll see some techniques for different functions. We'll actually start to see these functions in terms of their expression rather than their picture. And we'll try to tie that in with what we were doing here visually. I'll show you some plots in Desmos. I'll show you visually what these different functions look like so that we can link that with what we just did here with all of these visual limits.